the procedure for finding the acceleration vector is very similar. Of course, the acceleration vector is the derivative of the velocity vector. So what we need to do is take the result we just got and do another set of derivatives. And this time we're doing derivatives on theta as well as on omega. So we can think of it as theta in time as well as the change of omega in time. So to do the math quickly, we can find that the v dot equals, for starters, let's just do the theta. It would be negative r cosine theta instead of sine theta, cosine theta in the direction of x. And instead of plus, we end up with a minus r sine theta in the direction of y. Now we have our initial omega to add in, and because we're multiplying again by d theta over dt, we end up with another omega, so instead of just one omega, it's omega squared. Now for the second part of our procedure, we'll do the change in omega over the change in time. And because we're not dealing with theta, the initial part of our equation stays the same. Those are our findings of the velocity vector. So we can write negative r sine theta x hat plus r cosine theta y hat. And the derivative of omega is going to be alpha. So alpha is the derivative of omega, which is the derivative of theta. Therefore, alpha is the second derivative of theta. And you go from the position of the angle to the angular velocity to the angular acceleration. That's the relationship between alpha, omega, and theta.